This is Honors Algebra 2 Pre-Calculus, section 6.4 in Pre-Calc, but we're actually doing some physics stuff today. So on page 446 of your textbook, there are two formulae for finding the work done by a constant force F as the point of application, like where the F is being pulled from or pushed from. It moves along the vector PQ. So we're going to do an example from the text because I am totally not a physics teacher, and that's fine, but it's out of my wheelhouse to make up a ton of physics examples because it's not really my jam. So on page 446, there is an example. It's example 8 in the book, but it's probably not example 8 in these videos, so I just called it an example from the text. To close a sliding door for a barn, a person pulls on a rope with constant force of 50 pounds at a constant angle of 60 degrees, as shown terribly in my figure and much better on page 446. Find the work done in moving the door the 12 feet, this 12 feet, to close it. Now, a couple things here. Number one, having grown up on a farm, this is not where you would put the rope to pull the door. When you have a really heavy barn door, you want to pull from it at essentially your wherever your arm height would be for you to pull so that you're pulling straight across, right? Because essentially what's happening here, just to explain the physics of this, is that a lot of my effort is being wasted because I'm pulling both down and over, right? And that's not sensible because although I'm putting 50 pounds of force into this, not all 50 pounds are actually doing what I want, which is sliding the door closed, which would be a horizontal motion. A good portion of my work is actually totally wasted and is pulling downward, which is not what we want. So if you were actually trying to close a really heavy door, you would want to try and pull straight horizontally, like you want to pull in the direction that you want the door to travel. You don't want to pull at an angle because you're wasting some of your effort. But let's walk through this. So if you look at this first formula, right, so there are two ways to find work. You can either find work by multiplying the magnitude of the projection of F onto PQ. And again, just to translate what this means, this is the part of your force. This is the part of F that is actually doing the job, that is actually helping, right? So what I'm saying is that by pulling at this angle, if I were pulling straight across like this, I'd be actually just straight up using every bit of effort I have to accomplish the task. Here, I'm wasting a lot of my effort by pulling down. So this is the part of the force that is actually relevant, and then this is the direction, the magnitude of how far I have to pull it. So in this case, PQ is 12 feet long because I have to pull the door 12 feet, right? So it's how the distance that I have to, or the magnitude of what I have to do. So the other way to do is to do F dot PQ, but I'm going to argue in this case it's much easier to pick the first formula. So there are probably different times. Again, I'm not a physics person, but there are probably different times for each one. But I'm going to walk you through how we can figure out this one without using that crazy formula that was on page 444 for the projection. Sorry, that's an F, my bad. Okay, so one of these two quantities we already know, right? From the diagram, I know that the magnitude of PQ is 12 because this is physically how far I have to pull it, and PQ is 12. I need to pull this door 12 to close it. I'm going to be able to find the part of the force that's actually relevant to my world. If we look for a second, I'm going to try and inch over here and do this for a second. Essentially, what we're looking at is a triangle that has a hypotenuse of 50, and then the other angles are 60 and 30. Now, you could do this with, if this weren't a 60, if it weren't a nice convenient thing that both occurs on the unit circle and also is a 30, 60, 90 triangle that we all memorize for SAT prep, then you would have to do, essentially you'd say, okay, I want to know this quantity. I'm just going to call this the X, right? I want this quantity. So in order to find that, I would essentially say, oh, okay, the cosine of 60 degrees, right? I could say cosine of 60 degrees equals adjacent over hypotenuse. So 50 cosine of 60 is my X. Now I'm going to show you another option here in a sec. The cosine of 60 is a half. So I basically get that direction, the amount of my force, sorry, it's a 25, the amount of my force that's actually helping is only 25 pounds. So essentially, half of the total force that I'm putting in is actually doing the job, and the other half is completely wasted, which is super frustrating, but it is what it is. So anyway, so half of my force is wasted. Now, there's another way to do this. If you remember your SAT triangles, a 30, 60, 90 has a ratio of 1 to root 3 to 2. So you also could have noticed that if the ratio of X to 50 is 1 to 2, then X has to be half of 50, so X is 25. Either way, you get that this projection is a 25. So essentially, the work done in order to close this thing is going to be the 25 times the 12, which is 300, and it's foot-pounds is the measurement for work here, okay, so foot-pounds. And you don't have to know that, because again, this is not a physics class, and I am not a physics teacher. But again, just to point out, If instead, like, and that's not the problem we were given, but if instead in green, let's say I wasn't dumb about it and I didn't tie the rope up here. Let's say I put a handle here and I pulled straight across. So here's me, look, it's at my arm height and I'm pulling straight across. If I'm pulling straight across with that same level of effort, that same 50 pounds of force, all 50 pounds are going to be going into the door and the door's going to close a lot faster, which is one of those situations where we talk again about mechanical advantage and where you grab something or what simple tools you use. So anyway, that's my fake attempt at being a physics teacher from page 446.